so today what I want to do is discuss some example. The first example which I want to discuss is tuning, because we will need this when we go into parametric amplifiers. Now, what is the meaning of tuning? Now, let me go back to KDP, which we had discussed some time back in second harmonic generation. So, remember in KDP, potassium dihydrogen phosphate, NO is greater than Ne. And for second harmonic generation, what we had looked at was if XYZ is like this, my propagation angle is in some direction making an angle psi with the optic axis. To maximize the nonlinear, effective nonlinear coefficient, what should this angle be?
45.
Pi by 4, 45 degrees, so that the effective nonlinear coefficient maximizes. Otherwise, as we found, there is a sine phi term coming, and that becomes 0 if you propagate in the xz plane or the yz plane. Okay, so we had looked at second harmonic. So what was the, so there are two wavelengths. One is the, for example, let me take second harmonic from 800 nanometers to 400 nanometers. So what should be the, for second harmonic generation, which wavelength is incident? 800 nanometers is incident, and that generates 400 nanometers. So what is the polarization state of the 800 nanometers that I choose? Remember this condition.
Ordinary.
We have to choose ordinary, because as the frequency increases, or as the wavelength decreases, the refractive index increases. So if I need to achieve, what is the condition that we had obtained? The refractive index of the wave at 2 omega must be equal to the refractive index of the medium at the frequency omega. So we had seen that this will happen provided I choose my omega like this, and then I get a 2 omega in this direction, polarization. So the 800 nanometers will be ordinary, and the 400 nanometers that comes out will be extraordinary. By choosing the polarization states and the direction of propagation psi making a particular angle, so what I will have to have is the extraordinary index at 2 omega of the wave propagating along a direction psi m must be equal to the ordinary refractive index at frequency omega, which is independent of the direction of propagation. So for second harmonic, I input waves at 800 nanometers, oriented as an ordinary wave, propagating at an angle making psi m with the optic axis. In order to maximize the nonlinear effective nonlinear coefficient, I choose the propagation plane containing k and z axis to be inclined at 45 degrees to the x axis. And so for example, for a given medium, I know how NO depends on wavelength and how NE depends on wavelength. This is the Selmer coefficients. Selmer equation tells me. So I use these numbers to calculate the angle at which I need to propagate so that I get phase matching. So let me take an example. So here what I do is, last time we had done for ruby laser, well, let me take another set of wavelengths. So I choose, so 800 nanometers is one wavelength, and the second harmonic is 400 nanometers. So remember this equation we had obtained? Sine square psi m must be equal to 1 by NO square of omega minus 1 by NO square of 2 omega divided by 1 by NE square of 2 omega minus 1 by NO square of 2 omega. So what I do is, I'm given, for example, so omega corresponds to 800 nanometers and 2 omega corresponds to 400 nanometers. So I have these numbers. NO at omega is equal to 1.5015. NO at 2 omega is equal to 1.5238. NE at omega is equal to 1.4633. And NE at 2 omega is equal to 1.4797. So I've calculated these from a Salomon equation, and what I get is the angle psi m comes out to be 44.69 degrees. So this angle is different from the angle we had obtained earlier because that was wavelengths were different. Okay, that was 694.3 nanometers, the ruby laser input wavelength, second harmonic of that, and we had got 50.5 degrees or so. So the angle depends, of course, on the numbers here, refractive indices. So if I take a KDP crystal, propagate at an angle making 44.69 degrees with the optic axis, and launch 800 nanometer as an ordinary wave, then I will satisfy phase matching, I will have a finite coupling coefficient, and I will get second harmonic coming out at 400 nanometers along this direction. The k vector is along this direction, and I can calculate the s vector direction, etc. from here. And I have the formula to calculate what is the efficiency. Remember, we had an expression for efficiency in terms of the nonlinear coefficient, in terms of length, in terms of the power of the fundamental, etc. everything. Okay, now the problem we are looking at is inverse. So what I now do is, if I want to look at parametric amplification, what should I do? The same problem I want to look as a parametric amplifier. So my input should be 2 omega and an input also at omega, which is a weak signal. So if I choose the same direction, because I am satisfying the phase matching condition, whether I launch omega and generate 2 omega or launch 2 omega and generate omega, the phase matching condition is the same. Because it is simply saying that k2 omega is equal to 2k omega. The phase matching condition is same, the set of equations are the same, delta k is the same. If I launch omega and generate 2 omega, the input condition, the initial conditions are different from launching 2 omega and omega simultaneously. That's all. There is only difference of initial conditions. So to study this as a parametric amplifier, what I should do is I launch 2 omega. That means I launch a 400 nanometer wave as an extraordinary wave propagating at an angle of 44.69 degrees with the optic axis. So what do I expect? So I take this lithium, the KDP crystal. Again, go back to KDP crystal. And my propagation direction makes an angle psi m with the optic axis. And I launch a 400 nanometers wave like this. Input. Okay, so this is again making an angle of pi by 4 with the x-axis so that I get maximum nonlinear coefficient. And if I simultaneously launch a 800 nanometer signal, so this will be a high power, 400 nanometers will be much higher power, 800 nanometer will be weak signal. So along this direction when they propagate, the 800 nanometer signal will get amplified or attenuated depending on the phase difference. Phi 2 minus 2 phi 1, if it is minus pi by 2, I get amplification. If phi 2 minus 2 phi 1 is plus pi by 2, I get attenuation of the signal. That means either if the phases are right, I go from 400 to 800 nanometer, or if the phases are such that phi 2 minus 2 phi 1 is plus pi by 2, the 800 nanometer signal goes to 400 nanometer. So either splitting of 400 nanometer photons into two 800 nanometer photons, or joining of two 800 nanometer photons to form one 400 nanometer photon, depends on the phase relationships between the two signals which are coming in. So I can have an amplifier, the same problem, I can look at it as an amplification, and this is the degenerate parametric amplifier because the two wavelengths which are interacting with the pump have the same value. There are two signals, one 800 nanometer photon, another 800 nanometer photon interacting with the 400 nanometer. So this is an example of omega p is equal to omega s plus omega I, where omega s and omega I are equal. There's only one signal coming at 800, but because this wavelength is double this wavelength, the frequency is half this frequency. So I have two omega by 2 photons coming in, interacting with this omega photon. Oh, this is a higher frequency photon, these are lower frequency photons. In spontaneous parametric down conversion, which we have not yet discussed, I don't even launch this. I just launch 400 nanometer photons into this crystal, and what I expect to get 800 nanometer light coming out. That is spontaneous generation of the lower frequency waves. Yes?
The direction should be all the same.
Because that is the direction in which phase matching is taking place. If I choose some other direction for 400 nanometers, I will not satisfy the phase matching condition. I'll come to this problem now. So, I can actually generate 800 nanometer photons, pairs of photons of 800 nanometer, by shining light at 400 nanometers along this direction. So, there will be certain efficiency of generation which we will calculate later, but this is what is called as spontaneous parametric down conversion or parametric fluorescence. So, I launch 400 nanometer and out comes 800 nanometer light from the crystal. So, there are the 800 nanometer signal photons are coming from splitting of 400 nanometer photons into pairs of photons. Okay, so now suppose I change this angle. I keep the 400 nanometer fixed and I change the angle. As I change my angle, remember what are the conditions I need to satisfy? In general, I will have omega p is equal to omega s plus omega I. If omega s is equal to omega I, then it is corresponding to the second harmonic, otherwise not. And then what is the other condition? So in terms of wavelength, what does this give me? If I write this equation in terms of wavelengths, not in frequency, wavelength in free space, this is 2 pi c by lambda. So 2 pi c will cancel off. So 1 by lambda p is equal to 1 by lambda s plus 1 by lambda I. Because this is 2 pi c by lambda p, 2 pi c by lambda s, and 2 pi c by lambda I. All wavelengths are wavelengths in free space. The other condition is phase matching. So Kp is equal to Ks plus Ki. So in terms of wavelengths, this will be 2 pi by lambda p into refractive index, let me call this Np, refractive index at the pump frequency is equal to 2 pi by lambda s Ns plus 2 pi by lambda I Ni. So which is nothing but saying this is one equation and the other equation is, let me write this explicitly, n of lambda p by lambda p is equal to n at lambda s by lambda s plus n at lambda I by lambda I. I have not written right now whether they are extraordinary or ordinary indices, but I know that if I take this example of KDP, these two must be ordinary and this must be extraordinary, because the higher frequency wave is extraordinary and the lower frequency waves are ordinary waves. Just this example. So this could be a situation. This is a situation where lambda s is equal to 800, lambda I is equal to 800, and I get lambda p is 400 nanometers, and corresponding refractive indices. These two wavelengths are equal, so these two refractive indices are equal, and this equation just tells me n at omega lambda p is equal to n at lambda s is equal to n at lambda I. Okay. Now, if I change my direction, that means if I have the crystal in which I am propagating at 44.69 degrees now initially, I change my angle slightly. When I change my angle slightly, lambda p is fixed. I am still launching 400 nanometers. I have not changed 400 nanometer. This refractive index will now change because this is an extraordinary wave. So let me write this explicitly now in our case. In our case, because the pump is an extraordinary wave, the extraordinary refractive index at lambda p comma psi, some angle psi by lambda p is equal to the ordinary index at lambda s by lambda s plus the ordinary index of lambda I by lambda I. Psi is some angle now. If I choose psi is equal to psi m, 44.69 degrees, the solution of these two equations, this one and this equation simultaneously, gives me, so if I choose lambda p is equal to 400 nanometers, and if I choose psi is equal to 44.69 degrees, these two equations solution gives me lambda s is equal to lambda I is equal to which is what I have done. I'm just giving the same result in a slightly different fashion. Please note these two equations, for a given lambda p, I can use the second equation to replace lambda I by lambda p and lambda s. Okay, so I can eliminate lambda I from these two equations. So I will have one equation containing lambda p and lambda s, and of course the angle and the corresponding refractive indices. So for a given value of lambda p and psi, I need to solve these two equations simultaneously to find what is the set of lambda s, lambda I which satisfies both these equations. There will be only one set, because if I replace lambda I in this equation will contain lambda p, psi and lambda s only, and for a given lambda p and psi, this will give me one value of lambda s, and that value of lambda s substituted here will give me a lambda I value. So what I need to do is, if I change my angle, I need to resolve these two sets of equations, for which I need to know how NO varies with wavelength and how NE varies with wavelength with the Salmier equations, and I solve these two equations simultaneously and get the new pair of wavelengths lambda s, lambda I which satisfies this equation. So what I did was, I took some arbitrary angle. So if I choose now psi is equal to 44.2 degrees instead of 44.69 degrees, and I keep lambda p as 400 nanometers, the pair of wavelengths which satisfy these equations comes out to be lambda s is equal to 700 nanometers and lambda I is equal to 933 nanometers. These are approximate in the sense that there may be plus with some additional point, some wavelengths, but this is just to give you an idea that if I choose my wavelength, if I choose my angle of propagation instead of 44.69 to 44.2 degrees, and I launch the same pump wavelength 400 nanometer, now the pair of wavelengths of signal and idler which satisfy these two equations simultaneously, the energy conservation and momentum conservation equation, is another pair of lambda s, lambda I. So what does it mean? If I take this KDP crystal and if I launch 400 nanometer wavelength at 44.2 degrees, I will generate a signal photon at 700 nanometer and an idler photon at 933 nanometer, which is spontaneous fluorescence or parametric fluorescence. It will not generate 800 nanometer now, because 800 nanometer wavelengths do not satisfy the phase matching condition for this propagation direction. There is another pair of wavelengths lambda s, lambda I which satisfies the energy conservation and momentum conservation equation, and this pair of wavelengths comes out to be around 700 nanometer and 933 nanometer. One will be less than 800, the other will be more than 800 because of this equation here. Okay? And so this is called the signal. The lower wavelength is called the signal, higher frequency, and the other one is called the idler. So what it implies is, if in addition to 400 nanometers, if I launch a 700 nanometer signal at this angle 44.2, I will amplify this 700 nanometer signal. I will not amplify 800 nanometer now. I will only amplify 700 nanometer. The wavelength at which the amplifier works has changed, because the phase matching condition and in that direction has changed. So if I take this KDP crystal, launch light at 44.69, it will be an amplifier for 800 nanometer wavelength. If I choose my angle at 44.2 degrees, it will amplify either the 700 nanometer or 933 nanometer. It can amplify either of them. It is my nomenclature to call one signal and the other idler. There is no difference between the signal and idler. They are two different wavelengths. By nomenclature, I call the signal as the higher frequency and the idler as the lower frequency wave. It is complete symmetry. If I replace lambda s by lambda and lambda I by lambda s, I get the same set of equation. There is no difference. I'm just calling one of them signal, the other as idler. So, this is called angle tuning. The wavelength at which the amplifier will work changes as I change my orientation of the crystal. So, as I mentioned, we will put this amplifier within a pair of mirrors and make an oscillator, a coherent source of light. The wavelengths coming out of this coherent source of light will be the wavelengths for which this crystal will amplify. So, if I choose the crystal to be oriented at 44.69 degrees within the mirror pair, I expect to get 800 nanometer coming out. If I rotate the crystal slightly to 44.2 degrees, then I will get 700 nanometer or 933 or both of them coming out. Both of them coming out. So, I can actually, it's like a tunable laser. It doesn't depend on energy levels. Remember, helium neon lasers, ruby laser, all these depend on energy levels of atoms and molecules. These are fixed. But here, I can tune. All I need to do is to change the orientation of the crystal, and now this is an amplifier for another pair of wavelengths, and hence I can make it oscillate for another pair of wavelengths, and I get the laser which is tunable. So I'll come to this tuning and the oscillator, etc. later, which is called the optical parametric oscillator. Yeah.
When we change the orientation of this 2 omega wave with the optic axis, then we need to ensure that accordingly the d vector also changes direction, because just changing the propagation, the direction in which it is polarized, it also has to be taken care of accordingly.
This is the direction of polarization or the d vector of the wave.
It doesn't, it also doesn't remain fixed as we change the sign.
No, it's like this. This is the pump coming.
Yeah.
My crystal is sitting here, okay? And I rotate the crystal. This polarization is fixed. The optic axis, I'm changing the orientation of the optic axis of the crystal by rotating the crystal.
Okay.
So automatically, because of the orientation, it's always an extraordinary wave. Because I am only rotating in that plane. I'm not rotating in any other direction. I'm just changing the value of psi m, keeping pi by 4 fixed. Everything else is fixed. Yes. Automatically, this wavelength becomes an extraordinary wave, now propagating in a different direction, and hence its refractive index will change. And because its refractive index has changed, the pair of wavelengths which satisfy the simultaneously energy conservation and momentum conservation equation has changed. Yes?
Sir, initially what we said that was, depending on the initial phase, we'll either get a signal amplification or signal attenuation.
For degenerate. For the degenerate case. In the non-degenerate case, I showed you that if I only put signal and pump, I will always have amplification, cos hyperbolic square gz. If I put signal and idler and pump, then it will depend on the phase of the signal and idler with respect to the pump. Otherwise, no. In the degenerate case, I do not have a phase insensitive situation, because when I put in 800 nanometer, I'm already putting signal and idler simultaneously. They are not separate. But in this case, if I only put this, or if I only put this with the pump, I have always amplification.
So why isn't the new wavelength that's been created? Why can't it be an extraordinary wave? Why we are not considering that solution?
Can somebody tell me? Why can't these wavelengths be extraordinary?
Because then there's energy on the momentum.
I will not be able to satisfy this equation. If this is extraordinary, this is extraordinary, this is also extraordinary, this will be not satisfied.
So, but then it will be only for negative crystal.
Yeah, this is for one particular crystal I'm looking at, KDP. If I take another crystal, there will be situations will be different.
Is that they can be maybe a size, but it can be small, not as large as that size. It can have some angle.
No, for example, suppose I were to check at 800 nanometer itself. If all were extraordinary, it's not possible.
So they can be at different angles, right? So the psi can be different. They don't have to be.
The direction of propagation, you mean?
Yes.
Please remember, I am writing a scalar equation for momentum conservation, but actually it's a vector equation. So if what I can have is possibly the pump photons are coming like this, signal photons are going here, and idler photons are going here. I must satisfy all components of momentum to be conserved. So I have not discussed here the general situation where the pump is going like this, signal is going like this, idler is going another different angle, completely different angles. It's possible. And there are situations where this happens very nicely. And I will come to this example one later on, because this is used to generate entangled photon pairs. This kind of a process in which the directions are all different. It's not necessarily, this is a collinear case where all the signal, the pump, idler and pump, everything is traveling in the same direction. But you're perfectly right, it can happen in any other direction, but then I need to satisfy the corresponding vector phase matching condition.
Don't they need to travel the same direction for amplification to take place?
Yeah, that's another problem. But suppose I'm looking at spontaneous parametric generation. There's no amplification. It generates automatically. It will generate automatically along all those directions in which I satisfy phase matching condition. And there may be more than one direction. And this I will come to an example later on. It's possible that the momentum conservation equation is satisfied for directions of propagation of signal and idler more than one pair of directions. And so I will get light in all those directions in which I am satisfying the phase matching condition. Okay, so this is one interesting example where I can actually keep the pump wavelength fixed and I change my angle of propagation and I tune. Now, suppose I keep this angle and change my pump wavelength. What's going to happen? So suppose I keep the angle at 44.2 and change lambda p to 390 nanometers instead of 400 nanometer. Now again I need to satisfy both these conditions. Psi is known 44.2, lambda p is 390. The refractive index has now changed because the refractive index at 400 nanometer at 44.2 degrees is different from the extraordinary index at 390 nanometer at 44.2 degrees. Remember, 1 by ne square of psi is equal to cos square psi by no square plus sine square psi by ne square. So as you change the wavelength, the ordinary and extraordinary index change because of dispersion, and so the index seen by the 390 nanometer wavelength as it propagates along a direction making 44.2 degrees with the optic axis has now changed. If this changes, this pair of equations have to be resolved again. And what I will find is, I've got the solution now for lambda s comes out to be 725 nanometers and lambda I is so I can actually tune the pair of wavelengths by not rotating the crystal but changing my pump wavelength. If I change my pump wavelength, automatically I change the conditions of phase matching and energy conservation, and I will find a new pair of wavelengths which satisfy both the conditions simultaneously. So if I start from 44.69 degrees and launch 400 nanometer, I will get output light at 800 nanometer, or it will act like an amplifier for 800 nanometer. Let me look at parametric fluorescence. So I launch 400 nanometers at 44.69 degrees with the optic axis. I get 800 nanometer light coming out. And the polarization state of the 800 nanometer will be ordinary, because it is the ordinary index. It is the ordinary index at lambda s and lambda I which satisfies this equation, with the pump being extraordinary. If I change my angle to 44.2 degrees, keep the pump wavelength fixed, the output light now is at 700 nanometer and 930 nanometer. So the same pump photon at 400 nanometer now splits into a different pair of wavelengths. As I told you, this equation has infinite number of solutions. If I fix lambda p and I ask you what is lambda s and lambda I, it can be anything as long as this equation is satisfied. But I need to satisfy also this equation. And then I get only one pair of lambda s lambda I which satisfies energy conservation and momentum conservation simultaneously. So if I change my angle to 44.2, keeping the pump wavelength fixed, I get a new pair of wavelengths coming out, signal and idler. Both are ordinary again. If I now change the pump wavelength to 390 nanometer, then again the wavelengths change. Because again the phase matching condition is now different for another set of pair of idler and signal wavelengths. So this is actually tuning. I can tune the amplifier or the oscillator when I generate an oscillator by either tuning, angle tuning, or by changing the pump wavelength. There is also another mechanism which is called temperature tuning. If I change the temperature of the crystal, all the diffractive indices will change because the refractive index of a medium depends on temperature. So by changing the temperature from room temperature to 100 degrees centigrade or 150 degrees centigrade, I can actually change the indices and I can change these wavelengths coming out. That's called temperature tuning. So I can have temperature tuning, angle tuning, or I can change the pump wavelength and tune. So this tuning mechanism is very interesting, is important because I can, as I mentioned, I can make a coherent source of light like a laser. Starting from one laser at 400 nanometer, I can generate a tunable laser which emits wavelengths, and I can tune the wavelengths by adjusting the orientation of the crystal or the temperature or whatever it is. Okay, so this is one example which I wanted to discuss to tell you the flexibility that is available, and also note that the polarization states and the wavelengths of the signal and idler coming out are automatically decided by the phase matching condition and by the energy conservation condition. Now it is possible that you may not be able to find any pair of wavelengths lambda s lambda I for which both these can get satisfied. It's possible. And then there is no down conversion. I need to satisfy phase matching to be able to generate the two new wavelengths, the longer wavelengths, photons that are coming out. Tell me, if I launch 700 nanometer and 933 nanometer as ordinary waves along this angle, what will I generate? I launch 700 nanometer light, 933 nanometer light at 44.2 degrees, and these are both ordinary waves. What will I generate? 400 nanometer. This is the same process, and that's called some frequency generation. The frequency of this plus frequency of this is equal to frequency of this. And it is the same set of three equations. Only thing is, it depends on the pair of equations which I take to solve and the initial conditions. If I launch only omega p, it's parametric fluorescence. If I launch omega p and omega s, it is amplifier for lambda s and generating a difference frequency idler. If I launch lambda s and lambda I generate lambda p, which is some frequency generation. So those three equations contain all the three-wave interaction processes. This is called a three-wave interaction because there are three wavelengths which are interacting with each other to exchange energy through the nonlinear coefficient of the crystal. Okay, so do you have any questions in this? So I thought this was an interesting example that can help us understand how it is possible to tune the pairs of wavelengths and what kind of frequencies and wavelengths and polarization state that will come out from parametric down conversion. Yes, Ajib.
If only signal and pump are incident,
Yeah.
Signal will always be amplified irrespective of the phase of the signal and pumps?
Yes, which I showed you in the class. If it is non-degenerate. That means if these two wavelengths are different, then if I launch only this and pump or only this and pump, then this wavelength will always get amplified, irrespective of the phase of the pump and the signal. It always goes as cos hyperbolic square gamma z or gz. If I launch all three waves, then the phase relationships start to play a very important role, which direction energy is flowing, either from the lower frequency wave to higher frequency waves or higher frequency waves to lower frequency waves. Yeah.
So when we have signal and idler incident,
Yeah.
so, under these conditions, it would be like some frequency generation.
Yes.
Then what set of conditions should be there for difference frequency generation or something like that? how would it be different and what would be the conditions to that?
I am considering three frequencies which satisfy the equation omega p is equal to omega s plus omega I.
Yeah.
Okay. So if I want to study difference frequency generation, I will assume that the two waves which are incident are omega p and omega s, so that it generates omega I is equal to omega p minus omega s. If I want to study some frequency generation, I will assume that my input is omega s and omega I, which generates omega p.
So then over here 700 nanometer will be like omega p then if in case of difference frequencies.
Not omega p. Omega p is here, the highest frequency.
No, this is not being generated, right? If I am talking about these two wavelengths are incident, 700 nanometer and 933.
Yes.
And I want difference frequency generation.
Between these two.
Yeah.
Okay. Then one of them has to be called omega p.
Yeah.
Yeah. And the other one will become omega s. Yeah. But what I'm saying is, if I'm studying some frequency, I will call the waves so that the same set of equations. Otherwise, I have to keep track of what is the higher frequency, lower frequency, everything. But here, just by calling omega p is equal to omega s plus omega I and getting those three equations, I will call the frequencies by the corresponding names depending on whether I'm looking for some frequency or difference frequency or parametric down conversion, etc. Okay, so this is one example which I want to discuss. The second one which I want to see is the following, okay, which I want to look at in terms of quasi-phase matching. And let me take lithium niobate as the example. Now, lithium niobate has again NO greater than Ne. And let me look at the following situation. I have the crystal like this, and this is y-axis, z-axis. Now, I launch a pump as an ordinary wave. Okay, so what is the polarization state at the input? So pump is omega p and this is ordinary. So what is the polarization state? X, yes, this direction. Because if I propagate along this direction, the z direction is the extraordinary. Now this is the principal axis of the crystal. This is not the XYZ laboratory coordinate system. This is the principal axis, XYZ. So this is x axis. So omega p has X polarization. Now I want to find out whether this polarization, so what possibilities can exist? So omega p is incident. So incident is omega p and ordinary. Now, so I'm looking at down conversion. So there are three possibilities. So omega p ordinary leading to omega s ordinary and omega I ordinary. Now please remember, now I'm using quasi-phase matching. So I can choose an appropriate capital K vector to satisfy the phase matching condition. Okay, so I'm not restricted now to using birefringence phase matching. So I am taking the propagation to be along one of the principal axes of the crystal. In KDP, I could not do that. The other possibility is omega p ordinary giving omega s extraordinary and omega I ordinary. Omega p ordinary giving omega s ordinary and omega I extraordinary, which is the same as this, except that the names are different now. And finally, an omega p ordinary can give me an omega s extraordinary and an omega I extraordinary. Four possibilities. How do I find out which one can at all take place and under what conditions? Remember, I need to satisfy two conditions. One is phase matching and there should be a nonlinear coefficient coupling the polarization states. There must be an effective nonlinear coefficient, must not be 0. Please note, I must satisfy phase matching condition, which I can always choose by appropriately choosing the capital K vector, the spatial frequency of the nonlinear grating. But I must also have a finite nonlinear coefficient coupling the states. So now, let me look at the first process. So the first process is, what is the polarization state of the omega p? Omega p is expolarized because it is ordinary. Omega s is also expolarized, and omega I is also expolarized. So if you look at this equation which we had written earlier, the polarization pi is equal to 2 epsilon 0 di jk ej ek. These are total electric fields, total polarization. Okay? So I have to substitute Ej as a sum of the electric field of the pump, signal, and idler. Similarly, Ek, pump, signal plus idler, and I will find out what are the polarizations state generated. Now, this process I am looking at is coupling an expolarization of the pump, an expolarization of the signal, and an expolarization of the idler. So what is the nonlinear tensor element that will be responsible? D111. Okay, which is D11. Now let me write for lithium niobate. 0, 0, 0, 0, D15 minus D22, minus D22, D22, 0. Let me just verify I hope I'm not making a mistake. Yeah, that's fine. Yeah. Can the first process take place? D111 is D11. This last two ones are contracted to a single one. So D111 is actually D11, and that is 0. So this cannot take place. I may satisfy phase matching, but there is no nonlinear coefficient coupling the ordinary polarization of the pump and ordinary polarization of signal and ordinary polarization of idler. What about the second process? So the second one is, so omega p is ordinary. So let me write this. So this requires D111, which is equal to D11, 0. What does this require? So this is D1, omega is extraordinary. So 3, 1, which is equal to D1, 1, 3 is how much? 5. 3 is 3, 3. This contraction is 5, and that is not 0. Okay, D15 is finite. So I'll calculate now what is the period required, but before that, what about this one? D1, 1, 3, which is D15. 1, 3 and 3, 1 are the same. And what about this? D1, 3, 3. D13, 0. So these two processes cannot take place. Okay, so if I launch a pump omega p, which is ordinarily polarized along the y-axis of the crystal, propagating along the y-axis, I can either generate an extraordinary polarization of signal and ordinary polarization of the idler, or an ordinary polarization of the signal and extraordinary polarization of the idler. What will be the phase matching condition for the first process? So I'm looking at omega p ordinary, omega s extraordinary, and omega I ordinary. What will be the phase matching condition? So I'm looking at quasi phase matching. So remember, the general phase match quasi phase matching condition is Kp minus Ks minus Ki is equal to capital K. So this is 2 pi by lambda p into np, sorry, n, it's an ordinary index because the pump is ordinary. Ordinary index at lambda p minus 2 pi by lambda s into the signal is extraordinary. So extraordinary index at lambda s minus 2 pi by lambda I into ordinary index at lambda I is equal to 2 pi by lambda. The Kp corresponds to 2 pi by lambda p into refractive index of the wave at the pump frequency, which because it is an ordinary wave, it is NO of lambda p. Signal is an extraordinary wave, so minus 2 pi by lambda s NE of lambda s. Idler is an ordinary wave, so 2 pi by lambda I NO of lambda I. So let me call this lambda 1. Oops. Okay. What about this, the last one, the other one, where the other one is omega p ordinary, omega s ordinary. So omega p ordinary, omega s ordinary, and omega I extraordinary. So again I have 2 pi by lambda p, NO at lambda p minus 2 pi by lambda s, NO at lambda s minus 2 pi by lambda I, NE at lambda I is equal to 2 pi by lambda 2. So if I make a quasi phase match grating satisfying this equation lambda 1, so I know if I give you the pump wavelength, I can choose a pair of lambda s, lambda I which satisfies the energy conservation equation. For those lambda s, lambda I calculate the capital lambda 1 required. Similarly, I can also calculate the lambda s, the NO of lambda s and NE of lambda I and calculate the lambda 2 required. So if I make this grating of lambda 1, the input ordinary wave at omega p, the input ordinary wave which comes in polarized like this will split into an extraordinary wave signal photon and an ordinary wave idler photon. So what will come out is the signal will be Z polarized and the idler will be X polarized. The extraordinary wave is Z polarized, ordinary wave is X polarized. If I choose this period, the same pump photon at lambda p splits into a signal which is extraordinarily polarized and an idler which is, sorry, a signal which is ordinarily polarized and an idler which is extraordinarily polarized. And I'll continue with this example in the next class. We will calculate this lambdas required approximately. And so the interesting feature of this problem is I will again tell you what it leads to in a quantum mechanical picture, and it leads to some very interesting observations which I will again discuss later on when I discuss quantum mechanical principles. Okay, any questions? Okay, thank you.
Sir,
Yes.
In this process, we can choose the polarization of the output waves we want.
Yes, provided the corresponding nonlinear coefficient is non-zero.
Yeah, I mean,
Yeah.
answer 2 and 3.
Yes, we can choose.
You can choose.
Yeah. For example, I cannot have an ordinary wave coming into the pump and I want ordinary signal and ordinary idler. It's not possible because that's not possible.
Amongst which are possible.
Yes, because that is the advantage of quasi phase matching now. Because I can appropriately choose the lambdas required to achieve that down conversion process. In fact, I can choose the wavelengths. I can choose the polarization states also. Wavelengths also I can choose, because then the corresponding lambdas will change. That's all. Yeah.